Today we have a free talk of Sébastien Lefèvre and Pierre Adorni, who was Sébastien is a visiting professor in PhilAP from the University of South Brittany in France, and Pierre is a PhD student of his. And so, yeah, let's listen to Sébastien and Pierre.
Okay, so thanks, Ruben. Just checking where is the camera. Sorry for the technical issues. Okay, so just trying to see. Okay, try to have a presentation for you on site and you online. So I'm very pleased to be with you today. And so as Ruben was saying, so we are visiting you this week at PhilAP. Because actually activities at the PhilAP are very related to what we are doing in Europe, in France. So the talk is on training, and it's not only about training, but you will see, but about the question of sustainability with respect to foundation models. So it looks like a bit counterintuitive to combine these two, but we try to do research on this topic. So maybe before to go into the scientific details, just as a short introduction. It's not working anymore. Sorry, try to do like this, probably. No. Okay, technical thing, not for today. I need to, I think, okay, should be like this. Okay, here. It's this thing. Sorry. Oh. Okay.
Is that okay or no?
Yeah, it's okay.
Okay.
It's okay. Okay, we can remove this maybe.
Yeah,
no?
yeah.
Let you. Yes. Sorry for the technical issues. We will manage it. And it works. Okay, thank you. So, the real stuff. Yes, so I'm full professor at University of South Brittany. So Brittany is a western part of northwestern part of France. So you can see this on the map. So for those of you who are online as well, and I'm also having a visiting professorship position here at IRISA since now a bit less than a year, and I have also a position at the UiT, University of Norway in Tromsø, so very far north from here. So Pierre, he will have the second part of the talk, but he's doing a PhD on efficiency and geospatial foundation models, and we are both researchers in a group that is called Obelix. So I think for European people in the room, you probably know it rings a bell to you. So Obelix is a research group about 25 people working on AI for EO in Vannes, where we are located. And I see here in the room, so I can do some promotion as well on a master program that we are running with colleagues in Salzburg, in Austria. So we are running an European program, Erasmus Mundus Joint Master Degree, on geodata science and AI for EO. And yes, we have two people in the room here who are currently who know very well this, and probably some online, I saw. Also, in terms of activities that we are running in Vannes, there is a regional cluster in AI that is called Sequoia, and within this cluster, I'm actually holding a chair that is called Panoramics. So for those who are a fan of Asterix and Obelix and speak French, so Panoramics is the druid that does a magic potion, and for our English-speaking friends, it's Gadefix, but it's okay. The acronym is for planetary observation with research in AI for a mix of sensors and tasks, an EO sensor and task, and it represents quite well what we are doing in the group, trying to develop AI models or AI-related research that makes sense in Earth observation. So in Earth observation, we have specific kind of data we need to tackle. It's not the same kind of data that we have in computer vision, possibly specific kind of tasks. So it's far beyond only image classification, segmentation, object detection. We have tasks that are really usually more, different and then possibly more challenging. And that's what that is motivating us in terms of research. And maybe a last announcement here. So we are actually holding a spring school in a few weeks that is also on AI for EO, where registration are still open until the end of the week, so 3 days. And it is free, so just you need to cover your travel and your accommodation in advance, but then the participation to the school is free. So if you are interested, just you can check the website, and at the end of the presentation there will be a QR code. Okay, then our talk and a part of our research is about geospatial foundation models, and of course in the PhilLab I'm pretty sure that everyone knows about foundation models. Online, possibly a lot of people, maybe not everyone, but still a lot of people. And we can see this probably as a breakthrough in the field, as we had years ago with the introduction, a decade ago or a bit more, with the introduction of deep learning. That really changed the kind of research we were doing. So if I come back, so yeah, you are too old. I mean, maybe only 2 of us who can understand this. I'm not saying who is the other one. Some years ago, actually, there was a lot of research on what kind of features we should extract from remote sensing data. And then once we have extracted these features, then we can plug any machine learning classifier, for instance. Now, with deep learning, this has completely changed. And we have end-to-end learning, and so this was really changing the kind of research that has to be done. And I think that with foundation model, we go a bit in the same kind of change, where we actually will benefit from a generic model that we can actually fine-tune, or we can plug with some specific decoder, for instance, to deal with specific tasks. It's a field of research that is quite increasing. So there are many papers, and even, if you take only the one that are really significant contribution to the field, it's maybe more than 100 in 4 years. So suggestion also for PhD students or master students who are in the room and who would like to work on this topic. There is a lot of competition. Fortunately, I think the community is structuring, and there are ways to communicate and discuss. And I would like to, it's not because I'm here in the Frascati in this room today, but I really would like to mention and to highlight actually the role of the PhilLab in this, with, for instance, the workshop last year between IRISA and NASA here in Frascati on foundation model, where we, a meeting with about 300 people on site. It's something very huge on a topic that is just coming. Okay. You have here on the right of the figure just a figure from one of Pierre's paper on the different models that exist over the last years, and the mean performance they can get on benchmark data with respect to the publication date, and then the pointer. There is a laser. It's just left and right, or do I have a
just left? Yeah, I don't know. I'm sorry. I just use left and right.
Okay.
But,
okay.
Maybe you can.
No. Okay. No. It's okay. It's okay. Yeah. So you can see then the size of the models and you can see that, of course, more recently, more models of increasing size were popping up. And this is something that we are really concerned, and it's a question that is motivating the kind of research we are doing in the group. Is that, okay, it's very, geospatial foundation models, they are very promising still, and there have been scaling laws that have been established. So I think there have been some work here also in the PhilLab with some people who are here and some who've been to the other part of the ocean. About scaling laws. So we have shown that actually more complex model with larger parameters get better results. But here, so thanks to Pierre, so in this slide, you have, for instance, an estimation of the number of GPU hours depending for different models, and okay, you can see that the number is increasing largely, and even actually, if you compare the Dinovis 3 with more than 60,000 GPU hours with the H100 GPU, it's of course much more than the V100 GPU. I mean, it's much more powerful. So even these numbers are not completely comparable, and it's really exponential. So if once I will finish, I will give the floor to Pierre, and at the end you will see that it's possible to train a model with only 79 H100 hours. So just wait for him to explain what he's doing. So the presentation is organized in 3 parts. So everything really related and motivated by this question of sustainability for foundation model. I will start with a discussion on how we can benchmark geospatial foundation model in a sustainable approach, with a sustainable approach. Then I will talk about fine-tuning, always in this perspective, and then Pierre will continue with the training part. Just taking time. Okay. So there are many, as we say, there are many foundation models. There are many foundation models. So the question can really be how to decide which foundation model is the good one for my specific application, for my specific task. And so it's not always easy to compare, because there are various geospatial foundation models with different properties. There are various datasets also with different properties. So maybe ideally it will be to say, okay, let's try. If I want to understand what are the best geospatial foundation model on my kind of data, maybe I need to retrain all my foundation model on various datasets with this kind of data, but this is completely unrealistic. Okay, you remember 100 foundation models, many datasets. This is definitely not realistic. So there are, of course, several benchmarks that exist, and I think so. Pangea is really one of the two, I will say, leading ones. So this is very nice, but I mean, it's not possible to have every model in Pangea. I mean, it's beyond the effort, and even Pangea does not cover all the possible kind of datasets. So actually, one approach, and it's the first work from Pierre during his PhD. That is a PhD that is also jointly funded by CNES, the French space agency. So first work he did that was presented last year on this Morsi workshop in CVPR. It was about this question of benchmarking foundation model with an efficient approach. And actually, the idea is that maybe we don't need to retrain every single, I mean, it's not possible to retrain every single model on every single dataset. So why not to rely on what the author have already done and published in their papers? Okay, so in some papers you have some result. So this group has developed a foundation model. They have assessed the foundation model on several datasets. We should rely on this information. And the idea is that you can okay, the quality of the slide is not very good, sorry. We can design actually an approach where we put actually the foundation models and the dataset and the task into some kind of feature space where we actually will try to see actually if for a given dataset you have some result in terms of okay, this foundation model got this result, this other got that result. You can actually normalize the result and identify for one given dataset which foundation model is best and which one is worst. And through this, you can actually embed this result in this vector space and to find actually so you can find actually you can put in the same feature space thanks to this approach, you can put foundation models and also the dataset of the task that were used on different paper, and you can embed this result into a feature space where, for instance, in this figure, in blue you have the dataset. When I mean dataset, it's a bit more specific than just a dataset. It's a specific downstream task that has been used for benchmarking. So given this amount of training samples, for instance, or given a given training test fleet, and or also a given metric, because then for a given dataset, you can decide to measure for instance, the performance with, let's say, mean IUU. You can decide to measure the performance with overall accuracy or F1 score, or some other metrics, and maybe the results are different. So if you take one dataset, one training testing split, one metric, you have one result for one foundation model, and you can actually see, thanks to the approach developed by Pierre, you can actually see you can actually, for instance, use this feature space, use a feature representation method like UMAP here in this example to identify some clusters that tell you, okay, these dataset are closed somehow in the results they have been published. These foundation models are also closed, and maybe this could help you to, if you have one dataset, to identify, for instance, which model you should use. Okay, so without retraining any foundation model, you just rely on the result that has been published, that has been ingested. So Pierre did a lot of work to ingest all this information into this feature space, and it allows actually to also predict on a new task, or not a new task, to predict on a data set the performance you could expect with a foundation model. Okay, so it's the result Pierre got during this work was that actually you can actually predict this performance with an error band that could be about 20%. So 20%, of course, is quite high, because then if I tell you, okay, my foundation model will get 60% or 80% of accuracy, I will not be the same. It won't be the same thing, but still, it's somehow working, and it is not requiring any pre-training. If it's readable here, if you look a bit at the clusters that have been shown in this slide, you will see that actually, yes, there are datasets that are actually having the same kind of features, like datasets that are, let's say, related to optical imagery, datasets that are related to Sentinel-2, they are, and the same for the model. So this is quite interesting and useful. And of course, this has to be updated. So this was a work that has been published a year ago already, and so it needs to be updated for the next the coming models. So time is flying, and we started a bit late. So I jumped to the second part, that is on the fine-tuning step, and actually, so this I will present you some of the work that is done by Giovanni Castiglioni, and who is from Chile. It's not from Italy, everyone could expect. So it's some work that has been presented in the Terabytes workshop that was organized last year in ICML. And okay, so this is a joint PhD thesis, and so the co-supervisor are also put on the title here. Of course, the work that is currently done on foundation models, the ideal goal is to have a model that is completely frozen, and you just work on the decoder or the downstream task. You don't retrain the model. In practice, as everyone who did actually experiment foundation model, you always see that actually, if you fine-tune even the encoder, then you get better results. Okay. So here the question on this study was to say, okay, how can we fine-tune efficiently, and how can you think of so there are many methods about efficient fine-tuning, but here it was just a study to see if what we should do when we try to fine-tune models when we deal with satellite image time series. And so the dataset that we were using was the PASTIS HD dataset. So it's 2.4 thousands of satellite image time series with about 30 to 60 dates. The dataset is having different sensors, but we are using only the Sentinel-2 data in this study. And the question was to see how the performance of what could be the performance of the model if we reduce the number of labels. So as it is done, for instance, with Pangea with 110%. Here we were considering 100% of the labels, but also 50%, 10%, and even 1% of the label. It's also the promise of foundation model. The idea is also that to say, okay, thanks to the encoder, we should be able to answer our downstream task, to have a model for a downstream task with very few labels for the downstream task. And when we say 10%, sometimes it's still a lot of labels, so we go even to 1%. And because it was satellite image time series, we took the 35 last dates for each series, and here we were actually trying to also subsample the number of images of the time series that you need when you train or when you fine-tune the model. So we did 35 instances, but then we reduced this number to 25, 15, 6, and even one image. With the regular, so you have on the figure here the temporal distribution, and so it's a regular the regular sampling, because of course if you take only the 6 most recent dates, you don't grasp the same kind of behavior than it was on the full time series. And I forgot to mention, but the task is crop segmentation. So we have a series and one annotation. Okay. So for this work, then Giovanni was doing comparison between 2 models that are Chroma and SSL4U Dino, and using as a decoder. So this is for the encoder part, and using as a decoder an UpperNet. And the thing that was interesting here was that he was actually questioning the fact that usually when you do so either you say you do a frozen encoder, and then you don't touch the encoder. When people do fine-tuning, of course there are different strategies to do fine-tuning, but I will say by default, then if you do fine-tuning, you say, okay, then let's take all my data to fine-tune completely my encoder. Here he was trying an approach where actually he was having different, even for the fine-tuning policy, he was having different learning rates for the encoder and the decoder. So if you put a learning rate of 0, it means that you don't actually learn or retrain the encoder. So it's a frozen encoder. If you take a learning rate of 1, then you fine-tune everything. And then if you take, and you can see in the table on the bottom, a learning rate of 0.1, it means that here is you have actually you put much less effort on the retraining or the fine-tuning of the encoder with respect to the decoder. And this so you have in the figure you have the way he was doing this, and because so it's a satellite image time series, so using Chroma or SSL4U Dino, we get one feature map, one embedding per image, and then these were stacked through an LTAE to that, and then next fed to an UpperNet to generate one map, because then it's crop segmentation with a single date. You have to compare. The task is to do crop segmentation on a single on a one image that corresponds to the full series. On these 2 tables, so you see a lot of results. So with 100%, so okay, maybe I move a bit here. 100% there, 50%, 10%, and 1%. And for each of them, you have subcolumns with a number of dates. It's a lot of things to read. Basically, what you can see is that, of course, when you fine-tune the model, it gives better results than when you freeze the encoder. So this is not really new, but it's something that has been shown. But it's very interesting to see that actually, if you use this fine-tuning rate of 0.1, for instance, then it gets a good result you can see actually, for instance, on this part, okay, so for chroma, for instance, where we get the best result always with 0.1 of FT rate, so with a learning rate that is 10 times smaller for the encoder with respect to the decoder. We get better results than the other configurations. And so I'm not going too much further on the result, but the general conclusion of this study was that if you have many labels, then your task-specific models, task-specific models like, okay, I forgot to mention in the previous years that we were actually also comparing with the UTAE supervised baseline. That was actually, of course, a good competitor, and it's a kind of result we also have. I think, and Pierre will show it as well. But typically with UNet, for instance, that is if you take a UNet trained directly on the downstream task, usually it's also competitive. So if you have many labels, then this kind of models they can compete with fine-tuned geospatial foundation model. So it means that, okay, there is still a lot of work in foundation models to really come with an answer that is not too costly and very attractive with respect to classical UNet or UTE or whatever. Then the question of this fine-tuning, we saw that actually it's something that is very important, because then you can see if you have read the table in the previous slide, you can see that actually the results were quite different depending how much effort you pay on the fine-tuning. And of course, I didn't detail this, but the temporal resolution and the label availability, they of course affect performance, and it has been shown on this. Okay, and finally, of course, if you have not too many labels, it's very interesting to have a lot to counter this lack of labels with more data. More raw data, and like, for instance, on this satellite image time series, more images, even for frozen geospatial foundation models. So I'm stopping now. Yes, I think we are already started a bit late, and so and I give the floor to Pierre, who will explain you his work on the last part. Pierre.
Thank you, Sébastien. So hello everyone. I will do the last section, which is sustainable training, and I will talk about this work, which is my latest work. It's called EOS-FM, Can an ensemble of specialist models act as a generalist feature example? So this work is not yet published, but there is a version on archive and GitHub, and I will update it soon, but right now it's a bit of an outdated version. It's online if you want to check it out. So first, as an introduction, this is the same figure that we have seen earlier. Basically, it just shows that lately the big trend has been to increase the model size and the dataset size, which is the trend that is, I mean, in all things deep learning. Basically, you see it in language, in vision, etc. Because it works well when you want to have a general purpose model, to have a very large model trained on a lot of data. And this is basically what we see. We have some results that show that the bigger the model, the best is the performance, and that's been established a long time ago. And it's basically the real path for building foundation models. So if you want to build a foundation model, typically you want it to get big, because that's where it becomes very general and very powerful. And typically people, when they do these big foundation models, they do self-supervised training, because the classical supervised training with labels has some downsides. For example, the labels are very expensive. So typically supervised data sets are smaller in size because it's very expensive to make them. And they are also very specialized. Typically, when you have a supervised data set, it's a supervised with like one task, like land use and clover, or tree canopy height estimation, whatever. But if you train a model on this, it will be able to do this task specifically well, and that's it. And that's the problem with supervised training. It's very difficult to assemble a single supervised data set that has very large variety of levels and different tasks. In contrast, the self-supervised training has no labels, which means you can make much larger data sets much more easily. And you can also have pretext tasks that are general purpose, like reconstruction, contrastive learning, and so on. And so that's how self-supervised training became just the most useful method for making a large pre-trained model. Yet we believe that supervised learning still has some upsides. So you can still extract some information from labels. First, there are really rich training signal. So in comparison to just reconstructing the pixels of an image, for example, if you have a supervised learning dataset, typically you have very rich information that has been extracted by human experts. That's very, very important. And we have a lot of task diversity. So individual datasets are typically very specialized, but if you take the whole body of different datasets that we have in remote sensing, there is a very, very large difference, very large variety of tasks. But the main challenge remains to do this implementation. How do we actually train a model on all these different datasets together where they are really, really heterogeneous? So some research efforts have been made towards supervised pre-training. So for example, we have these 3 different papers like MTP, SAMRS, and self-supervised pre-training, which go basically in the direction of large-scale supervised pre-training. And we also have some like self-supervised work that also includes some labels in some ways, like Terramine, Thor, and SkySense. The intuition that we had behind our model, USFM, was that if we have 2 specialized models, so for example, here on top we have a land use land cover model that can differentiate different images in the latent space, and we have another one which can only do canopy height estimation. That's it. Maybe we can somehow combine them or combine their latent spaces to have one single latent space that can do both these tasks at the same time. And the way we propose to do that is by using an ensembling architecture. So what we do is we have a bunch of different models here. So in practice, those are convex models of 3 million parameters each, so very small models that are trained independently on very different data sets. So for example, this one has learned to do flood segmentation with SAR data, and this one has learned to do land cover and then use segmentation with RGB data, for example. And when we want them to do a new task, solve a new task, we just take our new data, input this data to all of the models, which probably have never seen this kind of data before. And so individually, they are really weak on this new task. But altogether, we can use all of their weak features and fuse them together to obtain some kind of general purpose features that actually work well on most tasks. So let me talk a bit about this. So the idea of using an ensemble as a foundation model has multiple upsides. So first, the training is really cheap because you only train very small models. And so you can do so on very cheap hardware. And it's like very small data sets and stuff. And so because of this very small data sets and very small models training, you can do the federated learning very easily. You just have to ask different people to train different models and then you combine all together. And yeah, it has way less hardware requirements. Also, the pruning is free basically because due to the design, you can remove like half of the encoders from the ensemble and it could still work. And you can also easily adapt this model to your needs. So for example, if you need a model that is really good on a specific geographic place, you can just add more encoders in the ensemble that are specifically trained on this geographic space, and it should improve the performance. So for my implementation, I used a bunch of different encoders trained on different tasks. So this is just some visualization to help you see different kind of tasks to be used. So we use multiple different data sets, but in the end, I think there was 23 of them, 23 data sets. So we have classification, segmentation, change detection. We have synthetic aperture radar. We have Sentinel-2 multispectral. We have RGB. We have multiple different modalities. And this is the distribution of our encoders. So we have a lot of very high resolution data. We have a lot of Sentinel-2 multispectral, and we have a little bit of SAR. And we still have some questions about this, like which data sets should we use for training? How many is enough? Are some data sets more useful than others? And this is some questions that we explore in the ablations later. So the first component of this model is the band adaptation. Because since all of these models have been pre-trained on different types of data, it's not always easy to make any input work with it. So we do some kind of adaptation algorithm to be able to pass any input into this model. So we have like a physically based adaptation where we try to match as much as possible the inputs and the models. So if we have exactly the same band, we just pass it. If we have a close enough wavelength, we just pass it. And in the last case, where we don't have any similar wavelength, so for example, if our encoder was trained on SAR data, but we only have optical data, we chose to give the SAR data, we chose to give the optical data to the SAR encoder anyways, even though it might just output rubbish, because we think that in that way, we can at least get an output from the model instead of just the model not working at all. So that's, yeah, still a question. Then we have an encoder selection step. Basically, what we do is for each encoder, we attach a weight that is trained during each fine-tuning. So this weight is like dependent on the actual task you are performing with the model. And we do some kind of regularization that's written here on the left on these weights in order to allow only K encoders max for given tasks. Then we can play with this K. And that allows the model to select dynamically during training the K best encoders for the given task. And so, for example, typically if we have a task on radar data, it will tend to select radar encoders, stuff like this. Then after that, we have the feature fusion, because as you might have guessed, each of these encoders is a normal convnet, is a convex. So it has like a pyramid output of, you can see the numbers here, these are the number of channels in the output. So we have 40, 80, 116, 320 channels each. And so if we have 23 of them, it's a very big latent space, so it's not very usable as is. And so we do this feature fusion that kind of performs the needle in the haystack search in all of these very weak features and try to find the ones that actually solve the task. In practice, at the start of this project, we just try to not do fusion at all and just use the whole feature space directly to the decoder. And it actually worked, but it made the size of the decoder explode. So we tried to add this specific linear fusion layer, which is very small in practice. And it does not impact the results of the model. It's basically the same performance, but you can have a much smaller decoder with this. And so then we tested this on the Pangea benchmark. And we have some quite good results, actually. Like, as you can see, it's not always the best, but sometimes it's the best. And most of the time, it's not very far from the latest baselines like Terramine and 4. We did manage to get some results on the XView and Biomasters datasets, even though for the Biomaster specifically, our model was not very good, but we still managed to make them converge, so we added them. And we use this metric here that's called average distance to best, which is basically for each data set, you look at the best performance, and then you compute the distance to that best performance. So if you are like 2 points behind, your DTB is 2, and then we compute the average of that. So it's kind of a metric that I use to see how far from the state of the art you are on average. And we can see that our model is basically competitive with Terramine, with basically the same mean distance to best on 100% labels. And on 10% labels, we can see that we even have a bit of margin. And also quite an interesting result here. We can see that with full labels, Terramine is significantly better than 4, but on lower label is actually the inverse, so which is quite interesting. And yeah, we can see that even in the low data regime, the model is quite good. And you can see that there is 2 lines here. We have the EOS FM and we have the EOS FM small, which is a version in which I used the encoder selection with the pruning during the training, with a case set as 6. So we have 6 encoders only on this version. So we basically delete most of the encoders from the ensemble. And it makes for much smaller models. And in some cases, it even improves the performance. I don't know why, which is interesting. Yeah, and in most cases, it just doesn't change much the performance, although sometimes it changes dramatically. Like, for example, on the Biomasters dataset, we can see that with a smaller ensemble, it doesn't work at all. So it really depends. The training of this model, well, I'm sorry for the quality, but the training of this model is quite cheap, because if you would just sum up the training of all these specific models, we see that we have about 80 hours on one GPU. You can either do this training all at once on a large compute cluster, and you can do it in 1 day. Or you can do it on a single GPU, like on a laptop GPU, you can do it. If you do it sequentially and you are patient enough, you can train all the models one after the other, and then you have the complete answer after some time. And yeah, this training is inherently easy because you can pause it, you can resume it because it's like small chunks, which is quite nice. And also, as you can see, some of these encoders have much higher training time, like we have FireRisk and, for example, Mini-France here. And if we can find out somehow that these models are not really useful, we can just don't train them, not train, and then we can reduce even more the training time. So some of our ablation studies here now. These are some graphs of the number of encoders that we allow, and then the performance on different tasks. So on the left is, sorry, I should have put the, I put it very small. On the left is HLS band scarce data sets, and we can see that it jumps quite quickly, the performance, and after like 3-4 encoders, it doesn't move. So which means that on this task, using the full ensemble actually doesn't have a lot of usefulness. Whereas on the second task, which is AF for small farms, we can see that even after 15, 16 encoders, it still improves when we add new encoders. So it depends really on the task. Some of the tasks can be solved with a couple of encoders, whereas some other tasks can really leverage the full size of the ensemble. We also performed an analysis of which encoders were selected when we allowed only a small number. So on the left, you can see a bar chart of the number of times each encoder was selected. We can see that some of them were actually not selected at all throughout Pangea. So keep in mind, this is only on the subset of tasks that Pangea offers. So we didn't train on every single task on Earth. So at least for Pangea, the Mini-France and the 712MS on RGB didn't do anything. So we can safely remove them from the training without any inference, without reducing the performance. And we can see here on the graph the distribution in modalities of the encoder selected for different tasks. So for example, on the SpaceNet 7 here, you can see that we had 3 different very high resolution encoders selected. We had 2 different Sentinel-2 encoders selected and 1 SAR, which is a bit weird because SpaceNet 7 is just high resolution RGB, I think. And we can see that most of the time it's actually quite coherent, but sometimes it's really weird. Like for example, we have for AI forms for farms, which is a Sentinel-2 dataset, we have a bunch of SAR encoders that were selected. And for MADOS, it's the same. MADOS has a lot of very high resolution encoders, despite the fact that it's actually a Sentinel-2 dataset. So that was quite weird. And so we investigated that after. So this is what I basically see. Sometimes the ensemble chose to select some encoders that were actually modality incoherent. And so with this, we did this ablation where we handcrafted some subsets of encoders. So we looked at the data set and say, okay, this is Sentinel-2. We're going to take all of the Sentinel-2 encoders, maybe add some ImageNet or whatever, instead of letting it choose itself. And that was like the S2 here, the curated set of encoders. And we can see that actually it didn't improve on the validation performance. So even though it's completely incoherent, it actually works better than for us to force on the model to use the same modality encoders. Now some discussions on this work. First, in terms of computational efficiency, we compared the JFlops and the FPS of different models. There are not the latest baselines here because I did this before, but yeah. And so we can see that our model uses less flops in general than the large models. But despite that, in inference, it's about the same. Like if you compare to Chroma, for example, we have a lot more flops, but we have about the same FPS. And we attribute this to the fact that we use a series of convolutional neural networks instead of using a transformer, which is more optimized for like GPUs and stuff. That could be a case. And so even though the model is really fast at training, in terms of inference, it's about the same. It's not particularly better. Another problem with this approach is that the standalone feature extraction that you can do with most foundation models doesn't really work here, because the model produces a very large representations without the feature fusion. And so since the feature fusion is trained on a task basis, is trained for each task, if we don't have a particular task and we just want to extract features, we have a very, very large vectors that are quite unusable in practice. But this is a limitation compared to normal foundation models. So to conclude, our contribution was to show that we can obtain general purpose representations with supervised training, particularly with this approach of combining different models through an ensembling method. So we introduced this model, EOSFM, that has very fast, easy, and modular training, that has quite good performance compared to recent baselines, and that has this training time pruning that is basically free, where you can reduce the model quite easily at training them without having some specific distillation or whatever. And I think that's it. Thank you.
Thank you, Pierre and Sébastien, for the super nice presentation. Do we have some questions from the room? For either? Yes.
Just about the information. When you said we impose the encoders and didn't let it choose itself, what do you mean let it choose itself in that way?
Well, what happens actually when I do this encoder selection, I can show, I think, is during the training, we add new parameters into the architecture. We add one scalar parameter for each of the encoders, which is this top K weight. And we let it be optimized. And then we perform a top K on these weights. So the optimization process can choose to reduce the importance of one encoder, whereas,
and also for the weird encoders that were chosen that were SAR, but it's like an optical task. Would it make sense to also consider that maybe the tasks were the ones that were similar and not the modalities, or did that also
it's
not?
possible. It's
Okay.
possible. I mean, we didn't check that, but I mean, it's entirely possible that even though the encoder was trained on a different modality, it can still extract some gradients or some stuff like this from the images and still perform some task.
Because SpaceNet, if it's building detection and you might have trained on STAR building detection task, then maybe I don't know, maybe it could.
Yeah. I think it's possible. For example, I think the SpaceNet one, which is building detection on Sentinel-2, right? I think no, maybe. I don't really know.
No. It's higher resolution.
It's higher resolution, yeah.
It's max, I should be.
I think it's like 4 meters or something, maybe.
3,
4. But we have one data set that is also building detection, but on very high resolution images, like 0.5 or whatever. And it was selected for this.
There's also the agriculture one you might have, because the one you showed was like optical, but then maybe you also have tasks that are based on SAR. I'm not sure which are the tasks.
We have only one agricultural task in the training.
And it was optical.
Yeah. We don't have a lot of agriculture in the training, which is, I think, one of the weak points of the model. You will see that on the agricultural data sets, on some performs less good than others. And I think you can quite easily correlate the performance of the Ensemble with like the sets of training encoders, which is nice, which means that you can build yourself an Ensemble for your specific needs and it works. So.
Very cool.
I was wondering, so you did an evaluation study where you kept all the Sentinel-2 which were relevant for the task.
Yeah.
But did you actually apply the same model to that only a Sentinel-2 and see if it actually refined it and only selected 4 or 5 which were super relevant and the same that was selected when you put all the different modalities?
I'm not sure I understand.
Okay, sorry, maybe I didn't understand this way.
What we did in the evaluation study, we didn't touch the data.
No, you selected the layers. I mean, the encoders
yes.
you wanted to use.
Mm-hmm.
So you had the 30 encoders, some were SAR, some were high-res, some were Sentinel-2. And then you're like, okay, so this task which was Sentinel-2, let's only give it Sentinel-2.
Yeah.
But you could do the layer selection only on the Sentinel-2, right? And see if this reduced the same Sentinel-2 encoders that you had when all were together.
Actually, I did this. Actually, there was 3 lines here. The beginning. So you got the normal, also all available, and you select. There is the curated where you don't have to select, you just forced to use this.
Yeah.
And then there was this curated but free, where you have only the 6 encoders, but you can choose yet. So if for example, the optimization process wants to drop one of them and use only 5, it can. And actually what happens is with this version, it works as well as the selection layer free. So it worked better than the curated by actually dropping a bunch of these modality coherent ones. So it dropped a bunch of the Sentinel-2 I gave, and it used like only 3 or 4 of them, and the performance was on par with the normal.
And the selected Sentinel-2 were the same selected Sentinel-2 than when you had all the different modalities?
I mean, yes, but it's forced because I gave it only like 5 or 6 different, and so it was that or nothing. So it had to choose some of them, but it like purposefully dropped some of them also, and it improved the performance, showing that sometimes having the encoder inside actually decreases the performance of the encoder, despite the fact that the decoder is trained and it could totally learn to not use the features. But what I think happens is actually some of these encoders allow the decoder to overfit. So in the training, it improves the accuracy, but in validation, it drops because it uses some irrelevant stuff.
That makes sense.
Yeah. So, but I didn't put it here because I wanted to show that.
Yeah.
So it's on your part, Sébastien, but it's about Pierre's work. So
Maybe he can answer.
yeah, maybe he can answer. It's about the slide where you do the comparison, or yeah, exactly this one.
Yeah.
So my question is more like on the validation. So how did you validate? And also, is there a point in validating with other things? Because for tabular data, for instance, there's loads of different tabular data, there's loads of different tabular data sets. We could do the same type of work and see if your method actually aligns better or not.
Yeah. This is basically like multi-dimensional scaling. So the statistical methods applied to financial models for remote sensing. So it's like widely used, I think. This specific implementation that I did, I don't know if it was reused. I didn't find in literature, but it's very similar to what's like tabular data set people do. What we did for validation here is, you can see on this graph, for example, you have so-called near crosses, and the crosses are validation points. So we did not put some of the models and some of the tasks in the training data. We optimized the latent space, and then we later added them and see, whether the distance between the points actually reflects the performance or not. And you can see that, it's not very visible. I should have put only validation. Yeah, but it's a little bit more spread out. You can see some crosses outside. So the validation does not work as well, but it still works. Like most of the crosses are inside. That's why you cannot see them actually. So it works, yeah. And as you can see, this error was computed actually on the validation data. It's like 20% on the relative performance, which is computed by doing min-max on the all literature performance. So for example, for Potsdam datasets where the performance go from 85 to 90, you have 20% on this range. So it's like basically 2%. Yeah.
It's not that bad.
It's not that bad.
40 was much worse.
It's not that bad.
So how do you concretely add a new data set in this embedding space?
So what you would do is you would, for data set, for example, you would take a couple of models that you see are far apart, like this model, this model, this model, whatever. And you train them, and then you add them to the data. Kind of a triangulation, And then you will have like results like pseudo results for a lot of data sets at once.
Cool. And I have a question. Yeah, about the last part that you presented. So you in the 23 data sets are included, maybe you said this in that case, I'm sorry, but are included the evaluation data sets or no?
No, I don't think so. I think I just did the training data. No. Only training.
Because in one way, you could do this, but on the evaluation data set.
For sure.
And probably if you add all of them, you're going to outperform many of the foundation models, no?
If you add the validation data set of these data sets to the training as well, I could just increase the size of the training data for free, basically. Yeah, I could have. I think when I trained this,
I will try this, and you will have great performance and show that everybody it's a simple thing to do, no? But then, of course, the continuation of the question is that the point of doing these evaluations on foundation models is that you hope that it shows that they could do not just those tasks, but any task.
Yeah.
So then you would also need another evaluation kind of where you evaluate on tasks that are not in your training set, but close to them or something like that? Yes, but now you have none of them. I think you could do many experiments making combinations where you show that you go for if they're all in the training set, and let's say you have 50, and then I don't know how many there are, then you will have super good performance, and then you can show how far you go by taking out some, I don't know.
So what you mean like testing the ensemble on these data sets themselves? Okay, so showing that one single model trained on it versus this single model plus 50 others actually was better?
Yeah, but you can do this for all the data sets in Pangea, for example, because the ones that are typically in benchmarks, which is a bit cheating, but in another way, no.
Like you mean training on the Pangea data sets?
Yeah.
I mean, yeah, I could have.
You include them in this set.
I could have, but I chose not to in order to have a thin separation between. But I mean, even though I did that, some are kind of close a little bit, because as you can see, for example, we have a bunch of language and cover datasets, which do not cover exactly the same enables and the same, but it's still similar to.
But I would be curious between two about that performance as well, and then about the difference between doing that and not doing that.
I mean, difference between adding basically training on the test set or not training on the test.
Yeah, but in a way, it's not really the test set because you're also fine tuning on the evaluation data set. You're not training on the test set of the evaluation data set. But and so it's
But for sure. I think it's an interesting experiment. Yeah.
The difference is that then you're not as much testing the generalization to other similar tasks. But
gives also a good comparison with the unit design.
Yeah, sure. Yeah, I wanted to show that generalization can arise from specialization. And that's why I did that. But I think it's also an interesting experiment.
It makes sense what you're saying. Does anyone else have a question? Or maybe
a quick question. So you have this one threshold where an encoder is chosen in the ensemble or not, right? Like this is not learned, but this is like the hyperparameter you have to decide on when you set up the architecture. It's
not exactly the threshold. It's like you keep the k highest weights. So you choose a k, like k equals 6, for example. We keep the 6 best encoders. And then whatever the optimization decides, it's forced by regularization to keep k weights above 0, and all the others are pushed towards 0 with a strong regularization. So in the end, it's forced to select exactly k encoders for the task, and you can select that. You can choose k whatever you want. It's not like it's not exactly the threshold. Is it clear?
Does someone online have a question? You can also put in the chat if that helps.
Sure.
You have to keep an eye on the chat.
I'm not sure where the chat is.
Sorry. Not a Teams Pro. Okay, so we have one question online. How did you choose the number of epochs for each data set to train your model?
It's a good question. I thought that actually whether the trained encoders are really good at the task or state of the art or not was not actually the main question, because if they did the task well and then they generalize well to other tasks was actually my main goal. So I didn't do too much like hyperparameter tuning and stuff on the training. I just trained until, like a typical deep learning fashion, until the curve started to look like a flat line. And when it stopped basically increasing validation performance, and then I just stopped the training. I don't know if it's clear enough. Thank you for your question.
If no one else has a question, we can more or less wrap up. So I'd like to So thank you very much, Pierre and Sébastien, for the nice presentation. Thank you, everyone, for attending. Also, thank you, everyone online for attending. And see you next week, in 2 weeks.